There we go. Wonderful. Thank you so much for joining us, everyone. My name is Mirka, and I'm the Director of Education at the McAuliffe-Shepard Discovery Center. And we are so happy to have you again for another virtual Superstellar Friday. It's been a little while since we've talked about the skies. So I asked our own Dave McDonald, who's probably forgotten more about the sky than I have ever learned, to do a session looking at the spring sky and kind of helping us see things. I know that today and last night especially was pretty rough looking for anything in the sky, but hopefully going forward we'll have some nice clear nights. Just as a reminder, we've got the chat so that if you have questions as we're going through, you can put them in the chat and I will feed them to Dave when he pauses. There's also the Q&A option. And remember with the Q&A that you can put a question and then someone else can see it and say, oh, I have that same question, and essentially vote for it to kind of get it to the top of the list. And so Dave will be talking, and then periodically I can send all of that to him, but obviously you can also wait until the end as well. So what I'm going to do is I'm going to mute myself and stop my video and turn it over to you, Dave. Thank you so much for doing this.
My pleasure, Mirka. It's always great to be able to be here at Superstellar Fridays to share, whatever the topic might be. And I love talking about the night sky. And it's hard to believe, where did March go? Today's April 1st. And I really don't know where March went. I know it's crazy. But anyway, we are in the first full month of spring starting today. And I'm going to share with you a lot of aspects about the night sky, which are good information for any time of the year, just to learn a little bit about what are you seeing when you look up at the night sky and you see stars and constellations and such. And then we will get specific about the sky in April. And of course, I don't know if it's going to come to pass, but my weather report said around 9 o'clock tonight, it might be clearing to partly cloudy, and maybe you'll have a chance to go out and find some of the things that we were talking about. But as far as planets, and I think most people really like their planets. And I love the planet Pluto, but unfortunately we can't see. It's so small, so far away. But in any case, the planet story really happens in the morning before the sun rises. And I'm going to share some pictures with you, some illustrations from Stellarium of different nights throughout the month of April that you might want to write down. And as Mirka said, there'll be access that you can go back and rewatch parts if you miss some of the dates and all, because this really is a great month for planets in the morning, which is kind of too bad for me because I'm not really a morning person. But there are a few nights during April that I hope, one, there'll be clear mornings, and secondly, that I'll be motivated enough to get out of bed and look at them, because there are really, literally, a couple of rare opportunities, and there's a rare opportunity happening in the evening as well. But I'll tell you more about that. So anyway, let me get started with my presentation. I'm going to share my screen. And as I do so, you may notice that I do have a lot of, tabs. I have a lot of stuff floating around on my screen, my desktop and such. So let's just see how this works. Okay, can everybody see that okay? Superstellar Friday, does that look okay?
Yep, we've got it. Thank you.
Wonderful. So just a little bit about me. I love astronomy. I teach astronomy for NHTI, or either I am or I have or will be. NHTI, Lakes Region Community College. I am a STEM and astronomy instructor at Belmont High School, where I currently work and teach. I am senior educator at the McAuliffe-Shepard Discovery Center. And you can find me there usually at least one weekend day. This weekend, it won't be tomorrow, but I should be there on Sunday. And at 3 o'clock every Saturday and Sunday, we have a Tonight Sky show where we talk about the night sky. and love to have you join in one of my shows, or on the alternating day that I'm not there is fine. And I'm currently a member of the board of directors of the New Hampshire Astronomical Society as well. So I just really love being involved in and sharing my love of astronomy with other people. And so our topic for tonight is understanding the spring night sky. And as I said, some of the initial slides I'm going to share, excuse me, will be applicable to any time of the year, and then we'll work our way in focusing on April and the spring. And hopefully, it will be clear tonight. So we'll talk a little bit about constellations, asterisms, distances a little bit, magnitude scale, which has to do with the brightness of stars, the colors of stars, what they mean, uh, kind of orienting yourself about the celestial sphere. What are we looking at when we go out and look up? And then what's up? Literally, what are the stars and constellations and planets that we can see now and during April? So constellations, we know, are a variety. There's 88 constellations in the night sky, which includes the northern and the southern hemisphere. This is a couple of pictures of constellations that are in the summertime, Sagittarius, and I put up Scorpius because it's very recognizable, very well known and such. And some of the constellations, particularly in the northern hemisphere, are related to mythology. And as we'll see in a little bit, the Arabs tend to focus on naming stars, and the Greeks and the Romans kind of invented, if you will, constellations that are related to their mythology. Asterisms. An asterism is a familiar shape which may be made up from stars from the same or maybe from different constellations. And the Big Dipper, it's a question I typically ask, is the Big Dipper a constellation? And the answer is no, it's not a constellation. It's an asterism. The Big Dipper is a familiar shape made up of stars, in this case, from the same constellation, Ursa Major. Then we have, and I'm going to show you a slide in a little bit, the Great Square of Pegasus. You've heard of the flying horse, the Great Square of Pegasus, an easy asterism to find, but the three main stars are from Pegasus, but we borrow a star named Alpheratz from the constellation of Andromeda to complete the square of Pegasus. And actually that star is the brightest one. So when we look up in the sky and we're looking at something like here, the Big Dipper, which is an asterism, we just kind of look at the celestial sphere as stars painted on some type of a spherical surface up there, which is what the ancients thought actually. But there's a three-dimensional depth to what we're looking at. And as you can see, my pointer's working here. The farthest star, this one here, is in the realm of about 120 light years away. Most of the stars, these 5 stars here, are in the realm of 70 to 80 light years away. And I have to say, one of my favorite stars is this one on the end. It's at the end of the handle of the Big Dipper, and it is 100 light years away. And I just kind of call it my century star. Whenever there's a century anniversary, I just look up at Alkaid. For example, just a quick, easy example, back in 2003, on December 17th, it was the 100th anniversary of the Wright brothers flying their powered flight aircraft, and which was December 17th, 1903. And so it was just kind of cool to go outside and look up and see this star Alkaid at the end of the handle of the Big Dipper. And as I looked at that star Alkaid, to realize I am looking at the photons, I am looking at the light that left Alkaid when the Wright brothers were flying their powered aircraft for the first time. It just chills up my spine. And then you notice on the background behind me, on the left of your screen, which is over my right shoulder, um, that is the Ingenuity helicopter on Mars. You may remember that the Perseverance rover landed on Mars February 18th, 2021, so just over a year ago, and it had a passenger on board called Ingenuity, and it's this helicopter that you see behind me, and it is the first aircraft. It's an aircraft. It's not a jet. It's not a lander. It's not a rover. It's an aircraft. It's a helicopter, and it landed on Mars, delivered by Perseverance, and it has made I think close to 20 flights now over the time. But one of the neat things is underneath the solar panel. So if I can use my pointer, I don't know, do you see me? If am I pointing over, do you see me? But the helicopter
Yes, we
is
can see that.
nice. Okay, so there's two rotors. They go in the opposite direction because this helicopter is not able to have a tail rotor to keep it from spinning out of control. So it has counter-rotating blades that are about 4 feet across. And then underneath that is the solar panel that charges the electronics, that charges the motors that, you know, make it fly. And underneath the solar panel of Ingenuity is about a 2 by 3 inch swath of actual fabric from the Wright brothers Wright Flyer airplane. Of course, with permission from the family and the museum, but that's just so cool that there's actually a piece of fabric from the Wright brothers' first powered flight on Earth on the first powered flight on Mars. Isn't that cool? The answer is yes. The stars appear to be next to each other, but again, it's just an effect of like a projection up there. They're really located at very different distances, and depending on what constellation you might be looking at, they could be very different. Here with the Big Dipper, we're looking from 70-ish to 120-ish light years difference. But some constellation, there's hundreds, yay, even 1,000 light years difference in the stars. And don't forget, the Big Dipper is an asterism. All constellations have borders. And one thing that I can't figure out is why are there so many jigs and jogs? You know, in the United States, when we think about how states' borders might be, and some of them are strictly by latitude lines or longitude lines. Some of them are contoured by rivers or by mountain ranges, and that makes sense. But when you look up in the sky, like what are the natural boundaries up there, and why are there so many zigs and jogs to make up these constellation boundaries? Only the International Astronomical Union knows. And they did this in the early 1930s. They divided up the sky into 88 constellations, just like there are 88 keys on a piano keyboard. There are 88 constellations in both the northern and southern hemispheres. In the northern hemisphere, in New Hampshire, we get to see around 67 or so constellations in the course of a year, 40 plus or minus in the course of an evening. We get to see more constellations in the winter because it's darker longer, and we see fewer constellations in the course of an evening in the summer because it's not dark as long as it is in the winter. So here are the boundaries of Andromeda and Pegasus, and you can see the square of Pegasus outlined there, and the star Alpheratz technically is in the boundary of Andromeda, and that star is borrowed from Andromeda to create the square. And as I said, an asterism can be made up of stars that are from the same or different constellations. I don't have a picture right now. I have a little bit later when we talk about a meteor shower, because we have a meteor shower in April, and we will have the asterism of the summer triangle, which all three stars that make up the triangle, triangles and asterism, are from three different constellations. Orion, so what we're going to talk about now is like naming stars. So Orion has at the top left star is Betelgeuse, very famous star. You probably already knew that. The bottom star, pretty famous as well, Rigel. As we look at Orion, the bottom right star, and it's bluish in color. I want to start to bring in the aspect of color here. Betelgeuse is decidedly reddish. Rigel is decidedly whitish blue. But in terms of naming them, you see these Greek letters, and maybe you may be familiar with oh, those are Greek letters. You may not know what they are, but you can look at them and say, I think that's Greek, and it is. And so Greek letters have been used to identify stars and constellations. There are 24 Greek letters in the Greek alphabet, and needless to say, constellations can have more than 24 stars, particularly when you start putting on binoculars and cranking up the telescope magnification. So stars all have a name, a Greek letter identification, or a numerical identification, which sometimes is alpha numerical identification. So all stars are cataloged in one way or another, but the brightest stars typically have a Greek letter identification, and Betelgeuse, the top left, is the alpha star, and the bottom right, Rigel, is the beta star. Typically, the letters in the alphabet go along with the order of brightness of the star. So you would think, just like the alpha dog, right, in a pack of dogs, the alpha star you would think is the brightest, and that's typically true. However, in Orion, we find that Rigel is just a tad brighter than Betelgeuse is. So nobody's going to change things around and mix things up, but technically Rigel would be the alpha star and Betelgeuse would be the beta star. And then you can see the other Greek letters: alpha, beta, gamma, delta, epsilon, zeta, eta, theta. I don't see theta. Iota here, kappa, lambda is up here, and etc. There's tau right here. And so typically, again, the brightness is in order of the Greek letter alphabet. So we would say, for example, Betelgeuse can also be said Alpha Orionis, and Rigel Beta Orionis is another way that you could name things if you were writing it or talking to somebody about it. So that's just a little bit about naming stars. And a lot of the names of the stars, as I mentioned earlier, are Arabic in their roots, because the Arabs seem to care about, and we're talking about back to Baghdad, Mesopotamia, Babylon, you know, back in the time when you had to watch TV by candlelight. And what are you going to do? Well, you go out at night and you lay on your back and you look up and you imagine figures, you imagine shapes, you imagine things, other people, mythological figures, and name stars. The brightest stars mean names. Well, Betelgeuse means armpit of the great hunter in Arabic. So Betelgeuse, if you looked at a image of Orion, you'd see the hunter. He's got his hand over his head or his arm up over his head, typically yielding a sword, and Betelgeuse fits that. Let me go over here to the right diagram here. Delta Orionis, that star's name is Mintaka, and Mintaka means belt. And so you have the three stars, very common. Again, in itself, that's an asterism of the belt of Orion. And Delta Orionis means belt. It's the name Mintaka. So this is a summer constellation in Libra, and Zubin Eshamali and Zubin El-Ganubi. And if we were talking about summer constellations, and maybe we'll have a superstellar sometime in the summer that we can talk about them in particular, but special names. This means northern claw, and this means southern claw, because the claws of the scorpion that I showed you earlier used to come out to these stars. And there's a story behind that. Stay tuned for more stories in the summer. Antares is the heart of the scorpion, very large, very red star. Back to the Big Dipper stars. When we look at them, we can see their names. Again, Alcade is the 100-year or the century star, I like to call it. The middle star, let's just talk for a moment about observing. So the middle star of the handle of the Big Dipper is actually 2 stars. That's right, 2 stars in one. And if you take time to observe, like we're not talking about you pop out your kitchen door onto your deck, you know, the porch light's on, the garage light's on, and you look up and you say, oh my, isn't that beautiful? Isn't that wonderful? Turn the lights off, dress warm so you don't feel like, particularly, you know, if it's chilly, and it's still going to be chilly for some time to come. But don't just go out for 5 minutes and look up and say, oh, isn't that nice? Put your coat on, your hat, turn the lights off, have a chair handy. Always have a comfy chair. Fold up chair is fine. But just even in the winter, I have a chair handy on my porch, on my deck, to be able to sit down and look up and enjoy the night sky and observe. And if you take some time to let your eyes get adapted, which is probably going to take 10 to 15 minutes of dark adaptation, and you look at the middle star of the handle of the Big Dipper, you will see there's 2 stars there. Mizar, M-I-Z-A-R, or Mizar, is the one that you just look up and there it is. But if you take a little time, you'll see there's a little companion star right next to it, and that star's name is Alcor, not to be confused with Al Gore, okay? A-L-C-O-R. And from what I understand, the Indians of old used to use that as an eye test. And if you could kind of just understand the difference, and you could see the difference of Alcor and Mizar, you would have good eyesight. And then you can notice that Dubhe or Dubhe is kind of reddish. That really doesn't pop red in the sky, but it is a reddish star. And if you took some time, you might see a little bit of a reddish hue there, but that's a more difficult red star to discern its color. But it does have reddish tones to it. So speaking of the color, this is a very, very, very famous diagram of stars, colors, temperatures, sizes, and such, called the Hertzsprung-Russell diagram, named after, guess who? A guy named Hertzsprung and a guy named Russell. And very famous. You will find this in every astronomy textbook. And easy enough to look up online. You can just refer to it as the HR or H-R diagram. And I just want to just share a moment with you about it, because we're talking about star colors now. And if you look down the bottom, you see temperature, and that K means Kelvin. So we deal with 3 temperature scales in science. One, the Fahrenheit scale, which is really not so much in science as it is us Americans just like to talk about Fahrenheit. Then we have the centigrade scale, which is definitely used by more scientists and is more used around the world. And so on our Fahrenheit scale, we know freezing is 32 degrees. We know boiling is 212 degrees. Yeah, why those numbers? I don't know. Centigrade scale, it makes sense. 0 centigrade is freezing. 100 centigrade is boiling. That makes a lot of sense. But then we have the Kelvin scale, and the Kelvin scale refers to absolute temperature, where 0 Kelvin means all molecular motion stops. And that is, there's no kinetic energy. And so the Kelvin scale, the size of a degree is the same as the size, if you will, of a centigrade degree. So temperature scale is in Kelvin, and you notice I should say 30,000 degrees, 20,000, I should say kelvins, because officially you don't use the word degree when you're talking about kelvins. 30,000 Kelvin, 20,000 kelvins, 10,000, 5,000, 3,000, 2,000. As we get cooler, notice the colors are going from blue to kind of a bluish white, to a yellow, to an orange, to a red. And so we typically think of red things as hot, right? When you go to a hotel room, the hot water has a red dot on it. The cold water has a blue dot on it. In your car, in the winter, you turn the temperature dial to the red for heat. In the summer, you turn the temperature dial to the blue for air conditioning. It's really the other way around. Those of you who may have wood stoves, particularly iron cast wood stoves, you turn the lights off, and it gets cooking. You get this cherry red glow, and you don't want to touch your stove. But if you let it get hotter, you'll see, well, it kind of goes from red to orange. And you don't want to go any hotter than that, but some people do. And if you were picturing an iron horseshoe, the person who's molding the horseshoe would have red hot, orange hot, yellow hot steel or iron to mold to fit the horse. But then beyond yellow, we get into white. And if you remember in chemistry, what color did you want your Bunsen burner flame to be? Your teacher would get that blue flame, because the blue flame is the hot flame. The yellow flame, it's hot, you're going to burn yourself, but the hot flame is blue, and yellow is kind of mediocre temperature for a burner, and it doesn't burn as clean. You get more soot and stuff like that. So the clean, hottest burning flame is the blue one. And it's the same with stars. At the top, I'm not going to belabor this one, but they're categorized O, B, A, F, G, K, M. And any astronomer worth his weight in gold could tell you that that stands for, oh, be a fine girl or guy, kiss me. And that's just how we remember the colors and the degree from hottest to coolest. Oh, be a fine girl or gal or guy, kiss me. Okay, so this is what's called the main sequence. That's where stars spend most of their time on. And then there's luminosity over to the left. Notice the 1, that's kind of a luminosity of 1 compared to our sun. So notice coming over towards the middle is where our sun is. And our sun is the definition of a luminosity of 1. And then when you get up to these supergiants up here, you see we're kind of at 10 to the 5th power. 10 to the 5th power is 100,000. So these supergiants are 100,000 times brighter, 100,000 times more luminous than our sun is. And then over to the bottom right, we have red dwarfs. You may have heard of them. And they are small, not so bright, cool stars. So these red dwarfs over into the bottom right of the diagram, you can see 10 to the minus 4th. That's 1/10,000th as bright as our sun, and the temperature being between 2,000 and 3,000 Kelvin. Our sun is about 5,600. And if you're a photographer, back in the day, well, maybe in a way still now with even digital cameras, what's the temperature of a sunlit, not cloudy day, but a sunlit panorama, a sunlit stage, something you want to take a picture of? You would set it to 5,600, because that is the color temperature of the sun. So that's related to the colors of the stars. And later I'll share some stars that you can look for their color. So I'll take questions after this slide. So this is just kind of a recap. Contrary to what we experience with heat and air conditioning controls, red stars are the coolest, around 3000 Kelvin. Orange stars are a little warmer, like Aldebaran, the eye of the bull, and that is 4000 Kelvin. I already mentioned Betelgeuse was red, around 3000 Kelvin. Yellow stars are average, around 5500 Kelvin, like our sun, and the star Capella, which rules the overhead sky in the winter, is kind of making its way towards the horizon. Now, white stars are really hot, like Mintaka. I showed you that pretty much the belt stars are white stars. They're really hot, around 10,000 Kelvin. Blue-white stars are hotter still, like Rigel. And then blue stars, and I've heard they have a kind, in a sense, a new category called electric blue stars, which are like really, really hot beyond 30,000 Kelvin. So let me stop there. Any questions so far anybody has?
There are not any questions at the moment that are in the chat, but I did have a question for you, just kind of looking at this scale. So I know it says yellow stars are average, like our sun, but when I look at the actual values, it's definitely toward the lower end of the scale, right? I mean, the difference between, 5,500 and 30,000 is pretty extreme. So is it just that those really, really hot ones are really, really rare?
Yes. Yeah. So average, you're right. I mean, if you're just doing math and you wanted to average, 30,000 and 2,000, the average comes out to 16,000. But most stars in terms of number
Yeah.
are kind of in this realm here. So that's a
Okay.
good clarification on the
Okay.
interpretation of average.
Okay. And then we have another question here, which is, what is a brown dwarf star?
Oh dear. Wasn't planning on that one. A brown dwarf is typically referred to as a failed star. It's a star that was going to become a star, and it had a good amount of mass. It got really hot, but it didn't quite ignite to become a full-fledged nuclear furnace star. So a brown dwarf is kind of like the star that never could.
Could have been a contender, huh?
Yeah.
Another question, how big can a star be?
Stay tuned. I will answer. If you don't mind waiting, I'll answer that towards the end of my presentation. I have that one in mind.
Okay, so those are our questions so far.
Samoli. So now let's talk about the brightness of stars. That's one thing that I think everybody notices when you go out on a dark, clear night and you look up. There's bright stars, there's medium stars, there's dim stars, and of course, there's stars you can't see. So there's this scale called the magnitude scale, which is introduced by this guy named Hipparchus. And in Greek, that's a Greek stamp with his image on it. Notice the star in his profile there. And this goes back to 160, 127 BC. The brightest stars, because remember, the Greeks were big into sports and the Olympics and such. And so you have a race. Well, who wins the race? The first place, right? And then the person who almost wins the race is second place, right? And so we have typically like first, second, third, fourth, fifth, sixth place, get some kind of a ribbon. And if you're later than sixth place, it's like, well, thanks for coming. So Hipparchus kind of did the same thing. And he said, well, the brightest stars will be first place stars. They'll be first magnitude. And the faintest stars that we can barely see, we'll call sixth place stars. And then, of course, the second, third, fourth, fifth place stars in the middle. And so that was his idea. And then he got his buddies together and he says, hey, Greek buddies, tell me, what do you think is you look at the brightest star and you look at the dimmest star, how many times brighter and again, we're talking, 100 years plus before Christ and all, and we don't have any photometric measuring equipment. We're just using our eyeballs. How much brighter do you think the brightest star is to the faintest stars? And they kind of, talked about it, and some easy numbers to come up with. Well, they came up with 100. They said, I think the brightest star is 100 times brighter than the faintest star. And there was some kind of a consensus, and so that was what was decided, is the brightest star, a first magnitude star, is 100 times brighter than the sixth magnitude star. And so there then became, because one thing that is true about Hipparchus and many of the ancient Greeks that we talk about, read about in our history books, in our math history, in our ancient physics history, is they're mathematicians, and they did figure a lot. Even though they didn't have quantitative equipment, they did have skills with mathematics and such. And so the fifth root of 100, like if you want to divide things evenly, so that multiply times multiply times multiply the same number from 1 to 6 and 100 times different, there's 5 divisions, and we want it to cover 100 times. So that's the fifth root of 100. So the fifth root of 100 is the difference between a first magnitude and a second magnitude, which is roughly 2.5. So a first magnitude star is roughly 2.5 times brighter than a second magnitude, and the second magnitude is roughly 2.5 times brighter than a third magnitude. And if you multiply the 2.5 times 2.5 times 2.5 times 2.5 times 2.5, you get to 100. Okay, so that's what they thought. But then what happens is we've got these stars now looking up in the sky. We now have equipment. We have photometric equipment that we can measure the bright. We can actually measure lumens. We can measure photons, and we can measure the brightness of these stars. And we come to find out, the brightest stars are a lot brighter than 100 times the faintest star. And so if we look here, we can see the naked eye limit is like right around 6, like we talked, and they decided, we're going to keep that the same. We're going to say that a 6th magnitude star is the bottom limit of human visibility under good conditions. And they also wanted to keep the fifth root of 100. They liked that scale. But now going to the left, we come to the star Sirius, which has a magnitude of about negative 1.42. But that's keeping to the same scale of fifth root of 100 from one magnitude to the other. And we get to a full moon, we're in the realm of negative 11 to negative 12. Our sun out in the daytime is in the realm of negative 26, negative 27 or so. And such. So, and then the Hubble Space Telescope can see down to like magnitude 30. And remember, a magnitude 6 star is at the limit of human visibility under really good conditions. And a magnitude 7 star is 2.5 times fainter than that. Okay. And if we go 5 magnitudes down to a magnitude like 11, then we're down 100 times fainter. So you can see when we get down to a magnitude of 30, those objects are really, really faint. And now we have, and maybe a topic for another time, the James Webb Space Telescope is up there, and its scientific instruments are being aligned and calibrated, hoping to do the first serious science in June. But it will be able to see even fainter than the Hubble Space Telescope's limit. So yeah, the full moon minus 12.5, the sun is minus 26.5, and that has to do with the brightness of stars. Polaris is our North Star, the star Alpheratz that I showed you that makes up the square of Pegasus is a magnitude 2. Antares, which is the heart of the scorpion, and Deneb is one of the summer triangle stars, is a magnitude 1. We have I should write in there Spica, okay? The star Spica, which I will be showing you shortly, is a magnitude 1. Vega and Capella are magnitude 0. Vega rules the summer sky overhead, and it's rising now in the east. Capella rules the overhead in the wintertime, and it's getting ready to set in the west eventually in the next month or so. It's a magnitude 0. Arcturus, which I am going to show you, is a magnitude 0, has a color of red. And Sirius, I mentioned to you, the brightest star in the sky is a magnitude negative 1.42. Jupiter and Mars, Jupiter is actually negative 2.1. Mars is fainter right now, but we assign numbers to the planets. And Venus, notice the negative 4.5. It's right now like a negative 4.1, but I mean, that's crazy bright, right? So in the morning, when you get up and you go out in the morning, that bright beaming light over in the east, that's Venus, magnitude negative 4.1 or so. Planets change sizes depending upon how close they are to Earth. Right now, Mars is pretty small, but it gets bigger as it gets closer to Earth and such. And so just recently in 2020, a couple of years ago, it was fairly large. And we're going to have another really good apparition of Mars in 2035. There'll be other good ones, but the next really good one will be in 2035. For our celestial sphere, when you look straight up, it's called the zenith. When you look straight down, it's called the nadir or the nadir. And then the north celestial pole, that's where we find the North Star. And I'm going to show you where to find that in a little bit. And the celestial equator, that's the equator on Earth projected up into the night sky. So that star Mintaka that I mentioned to you, that is the third star from left to right, the third star in the belt of Orion, that's pretty much on the celestial equator. So Orion's belt is really close to the celestial equator. Things move. So this is what we call a star trail, and you can actually do this with your camera if you can leave the shutter open for a period of time. I think some cell phones have this capability, but if you have a regular 35 millimeter DSLR camera, you should have what's called a bulb setting or an exposure setting where you can leave the shutter open for a period of seconds or minutes, and some even allow you hours. And so the North Star is right here in the middle, and it's right over the North Pole, actually about 3/4 of a degree off. And we have Ursa Minor, which is the Little Dipper, coming off of the North Star. The North Star is at the end of the handle of the Little Dipper, and we have Ursa Minor here, the Little Dipper. And you can see the Big Dipper over to the right. Ursa Major is the constellation that the asterism of the Big Dipper is in. And you can see the further away you get from the North Star, the larger the arcs. And if you could do a whole circle, the larger the circle would be going around the North Star. So Earth rotates in 23 hours and 56 minutes. And we have the tracings of the stars as Earth rotates. The sun moves. Well, it's really Earth that moves. The sun is stationary, although we as an entire solar system are moving pretty fast around our galaxy at around 250,000 miles an hour. Earth is on the move too. So on this red, purplish, pink oval there, that's the path of Earth. and Earth is moving 67,000 miles an hour. So it feels like we're standing still, but we're going 67,000 miles an hour around the sun. And it takes a while. Well, it takes about a year to get all the way around. So here we are in March. You can see March 1st. So April 1st is about where the arrowhead here is. And so during the daytime, we cannot see the constellation of Aquarius because the sun is in the way, because we're over here. But if we turn around and we look into the night sky, we see the constellation of Leo. We see the constellation of Virgo, which I'm going to show you in a little bit. So we see the night sky over here, and the constellations and stars that are lined up with the sun, we don't see them. They go away for a month or so, and then they reappear. But that's what happens as Earth goes around the sun. We have a different viewpoint on what constellations we can see and what constellations we can't see because they're blocked by the sun. And we call those constellations, by the way, the specific constellations that the sun appears to move through, zodiacal constellations, or the constellations of the zodiac. And the sun's apparent motion through the sky traces out a line we call the ecliptic. The ecliptics. Technically, the path of Earth around the sun, but since we're on Earth, to us, it appears as though the sun is moving, but it's really Earth that's moving. And the ecliptic is the projection of Earth's orbit onto the celestial sphere. So here, the ecliptic is kind of in that bluish line that is arced, and you see constellations of the zodiac there from this particular photo, which is taken up north. Notice there's some snow on the ground and there's not any trees. This is up in the Arctic somewhere. But the sun is in the constellation of Aries, and it will move through Pisces, Aries, Taurus, Gemini, Cancer, Leo, and through all 13 zodiacal constellations. And I say 13 because astrologers, of which astronomy is totally different. Astronomy is the science. Astrology is sometimes referred to as a pseudoscience. And they forgot about Ophiuchus. Ophiuchus is really a constellation of the zodiac, and the sun actually spends 3 times longer in Ophiuchus than it does in Scorpius. Somebody forgot about those things. So the planets and the ecliptic, the planets stay very close to this line, right? So the planets don't stray far, except Pluto can get 17 degrees away. Right now, it's pretty close. It's pretty close. Jupiter is close to the ecliptic. We can see it in Capricornus. We can see Saturn in Capricornus. Venus is in Aquarius. I'll show you that in just a little bit. So questions, and then we're going to get to looking at what you can see in the sky this week. But I'll just stop there. Any questions about magnitudes, planets, ecliptic, stuff like that?
So nothing has come through yet, but we'll give people a moment just in case they have any questions going forward. It was interesting for me to look at that picture of the, far northern sky and see how many of those constellations kind of spanned that space in a place where you do have a lot of sky up there to work with. So
you do.
That's very neat. Okay.
Okay.
So I still don't see anything, so I would say let's keep going.
All righty. Well, let's take a look at April 5th. That's coming right up. Okay, so that's this Tuesday morning before sunrise. Okay, before Dave McDonald gets out of bed. I hope it's clear, and I hope I do get out of bed. This is a rare opportunity. If you look down here, you say, "Oh my goodness, what's the matter with Dave? Look, he's got the, Saturn and Mars on top of each other. Doesn't he know that he should have those words separated from each other?" Well, The reason the words are on top of each other is because the planets are on top of each other. Those planets, Saturn and Mars, are a mere 24 minutes of arc apart. And you might say, oh, well, I knew that. Well, what does that mean? 24 minutes of arc. Well, we use minutes of arc to denote a distance in the sky that's small. So for example, and maybe you can identify with this, if you can picture a full moon up in the sky, okay? So the full moon is up in the sky, and from edge to edge, like if you want to make it like an equator, the line across the diameter of a full moon is 30 minutes of arc. It varies slightly depending whether we're at an apogee or a perigee, but on average, 30 minutes of arc. So these two planets, Saturn and Mars, are going to be closer together than the width of a full moon up in the sky. That's crazy. And you've got some time to get some binoculars. You'll be able to see it because Mars and Saturn are bright enough to see. But you also have to realize, you can see here that the sun is starting to be a contender, right? The sun is starting to light up the sky. So we're about 45 minutes or so before sunrise. The sky is starting to get light, which makes fainter objects harder to see. Binoculars are really, if you're interested in astronomy at all, I would really encourage you to get binoculars because they are a really, really helpful astronomical tool you can do a lot with. But get a decent pair. Don't spend $30 for a pair of binoculars. You want to spend at least 80 to 100 and it'll pay dividend. You can pay a lot more, but you just want to get maybe like a 7x, a 7 times, and a 50 millimeter, so 7 by 50 millimeter binoculars of a decent quality. Don't pay less than $80. So you have something that's decent, that's not going to be blurry and such. And Mars and Saturn will be a great binocular object. If it looks like it's going to be cloudy on Tuesday morning, but it's clear Monday morning or it's clear Wednesday morning, still take a look. They're going to be close. It's just that on Tuesday, it's their closest. Okay, and you can see that Jupiter is getting ready to rise at this time. Okay, so we're going to take a jump now. This is April 5th, so this is this coming Tuesday, coming right up. But then we'll take a jump to the 17th, okay, which is just about a little over 2 weeks away. Isn't this awesome? And again, we're before sunrise, and at the same time, because time is going on, the sky is a little lighter in the morning. This is around 5:30-ish in the morning. But look at the lineup of the planets: Jupiter, Venus, Mars. Look at how nicely they're lined up. It's a planetary alignment. Something spiritual is going to happen on that day. I don't know. But in any case, Jupiter is blazing, magnitude negative 2.1. So we're talking about easily 3 times brighter than the brightest star in the night sky. Venus, negative 4.1, which is about 6 times brighter than Jupiter is. Mars, it's around magnitude 1, bright enough, but not super bright. And Saturn. And if you have a telescope, it's worth taking a look. Mars has, we were talking about seconds of arc or minutes of arc. Well, a minute is made up of 60 seconds. So seconds of arc are smaller pieces, and Mars is about 5 seconds of arc, which is a discernible disk, but a small discernible disk in a telescope. And Saturn is about 16 seconds of arc, so it's about 3 times larger in a telescope, even though it's so much further away, because it is really so much bigger. But that's a great morning to look, April 17th. Now, same day, April 17th at night, another glorious thing to be able to see, okay? 8:15, the evening of April 17th. You can see we're facing west. You can see Orion over there, and you'll be able to see Orion in that evening. You can see Betelgeuse, red star, Rigel, blue-white star. You'll be able to see Aldebaran, orange star, magnitude 0, 0, it's close to 0, it's like 0.5. Betelgeuse of magnitude 0, Rigel 0, Aldebaran's of magnitude 1. Capella is yellow, magnitude 0. So the nice thing about Betelgeuse, Rigel, and Capella, they're all about the same brightness, but different colors. And Aldebaran is a little fainter than those three, but definitely has an orangish color to it. And you may want to go out or stay out a little later, let the sky get a little darker, because again, this is after sunset, and then the color will be a little easier to see. But what I'm showing you specifically are the planets. 8:15, April 17th, look at Uranus and Mercury. Mercury is by itself a project. You know, you want a project, you want something that's an astronomical quest, find Mercury. There are tons of astronomers. The vast majority of astronomers have never seen Mercury in the night sky with their unaided eye. And so you have the opportunity to find Mercury. But the story gets better. Right next door is Uranus. And Uranus is right on the edge of visibility on a dark, clear, moonless night. It's a magnitude 5.9. But in the glare of the leftover sun, there's no way you're going to see it with the unaided eye. But again, binoculars. So you got a couple weeks to get a decent pair of binoculars, $80 to $100, 7x by 50 millimeters. And you take your binoculars and you look 8:15 to the west. The brightest object you'll see will be Mercury. And then you won't see Uranus with the unaided eye, but get your binoculars and you're going to see, because there's a star that is about the same brightness as Uranus in that binocular view. And the one that's closest to Mercury, that is Uranus. It's about a 2-degree field. They're about 2 degrees apart, but close enough to be in the same field of view in binoculars. And if you had a telescope, it's a great way to find Uranus. You find Mercury, easy peasy, and then just a little bit to the left, just a little bit lower, you'll find the planet Uranus. And one way with a telescope, you can tell the difference between a star and Uranus is Uranus, being a planet, has a discernible disk. So you won't see a pinpoint of light. You'll actually see like a little small circle. And that's the planet Uranus, and the star near it will appear pretty much as a pinpoint of light. So that's exciting. I hope it will be clear, because I am typically up at 8:15 at night. So I hope to look at that one. Next, we're back into the morning, April 25 to 28, and it's the same lineup of planets, only every morning they're going to change a little. The reason I chose April 25, 26, 27, 28 is the moon is on the move. The moon will enter up here around April 25th, and every morning for the next 3 or 4 mornings, you'll just see the moon slide underneath Saturn, in between, under Mars, in between, under Venus and Jupiter. And the moon will continue to get a little more crescenty, a little more slender as it gets closer to the sun to become a new moon in not that many days from then. So another great thing in the morning. Then I want to jump to the morning of April 30th, because here's another what we call conjunction of the planets. We have Jupiter and Venus, which are the 2 bright ones. Jupiter minus 2.1, Venus minus 4.1, the brightest planets in the morning sky before sunrise, so close together. They're not going to be that close again for 17 years. So You won't need binoculars, but binoculars will still be cool to be able to see them. And a telescope is still going to be wicked cool to see them through a telescope. But even with the unaided eye, they're going to be so close. It's going to be so, so pretty. I hope it's clear. And again, if it looks like it's going to be cloudy April 30, April 29, April 28, May 1st, May 2nd, still worth a look, but April 30th is the closest approach. And then lastly, at the moment, are the Lyrid meteor showers. And I mentioned to you that I would show you the summer triangle, and here it is. This is 1 o'clock in the morning though. And the reason we're looking at 1 o'clock a.m. is because we're looking for meteors and a meteor shower. And the vast majority of meteor showers, you see more meteors after midnight because Earth is positioned in such a way that it's the front, if you will, I guess that's what I'm going to call it. The front of Earth is moving ahead through space at 67,000 miles an hour. So rather than the meteors having to catch up to your rear view window, they're kind of coming right at you in the front windshield. So that's going to be a good time. But again, April 20, April 21st, April 23, 24, whichever is a clear night is worth going out with a chair, shut the lights off, dress warm, hot chocolate, donuts, and enjoy yourself and stay out for an hour or so and just enjoy looking up at the sky. And at 1 o'clock, you can see the summer triangle. 3 stars making an asterism, the triangle, Vega from the constellation of Lyra, which is what the Lyrids are named after, Altair from Aquila or Achaia, the eagle, and Deneb, which is the top of the Northern Cross, or the tail of Cygnus the Swan. So you have the asterism of the triangle with stars from 3 different constellations, and you can see the summer triangle, which will become more and more and more prominent as we get closer to summer. But right now, you see the summer triangle at 1 o'clock in the morning. So there's that. And then I mentioned to you Arcturus, and Arcturus is over here to the left, and I'm going to show you an easy way to find that. So here is the Big Dipper, right top center. If you take the 2 stars, Merak and Dubhe, they point to the North Star, and that's the star that everything else rotates around. Here's the Little Dipper. This is Draco the dragon. And if you take the handle of the Big Dipper, it kind of makes an arc, and it arcs to this star Arcturus. Arcturus rules the overhead sky. It's magnitude 0, and it's reddish in color. And then if you kept coming down, follow the arc to Arcturus, and you keep on going down towards the horizon, you're going to come to this star called Spica, S-P-I-C-A. Spica is a magnitude 1 star, and it is a whitish blue star, magnitude 1. It is in the constellation of Virgo, the Virgin. Okay, so real quick, and then we'll be done. And then if you want me to go back and look at any constellations, we can. But those are key spring constellations. The Big Dipper, we look towards Arcturus. This ice cream cone shape is Boötes, the herdsman. I think it looks more like an ice cream cone. And then over here, Spica is in the constellation of Virgo, the Virgin, which the way it's drawn here kind of looks like a slug with antennas there. Somebody asked about star size. Well, we'll go through this fairly quickly here. Here's our sun. Here's Earth, right? Pluto is like a pixel. Earth, Jupiter, and there is our star, the sun. Well, here's our sun over to the left. There's the brightest star in the night sky, Sirius. Pollux is one of the twin stars. And here's the star I just showed you, Arcturus. Arcturus is that reddish magnitude 0 star. Arc to Arcturus. Look how much bigger Arcturus is than our sun. Well, then look down here at the bottom. That's Arcturus now. And Rigel, bottom right of Orion. Aldebaran, the eye of the bull I showed you, was an orange star, magnitude 1. And here's Betelgeuse. Betelgeuse, the upper left star of Orion. And look at, our sun is 1 pixel on this slide. And Arcturus is so much bigger and Betelgeuse is so much huger. And in the summertime, I mentioned it to you earlier, but it's a summer constellation, Scorpius, but Antares is amazingly huge. If you put our sun at the center of Antares, the star Antares would incorporate out through the orbit of Mars. Crazy. So that's what I have in terms of constellations, and there's some information about stars and sizes of stars. Before I close my PowerPoint, I'll see if anybody has any questions about anything I've shared, or maybe you have another question of something that you would like to see.
So Dave, we do have a question that doesn't quite fit in with this last bit right here, but Lorraine is wondering what made the Earth tilt?
That's a good question. And one of the things relative to the tilting of planets, because if you look at the tilt of all of our planets in our solar system, there's a variety of tilts. There's a sense in which, depending upon how you view it, Venus is upside down. All the planets rotate counterclockwise as seen from above, but Venus rotates clockwise, which leads some astrophysicists to believe it got kicked upside down. Earth has a 23.5 degree tilt at the moment. Uranus rotates on its side at like 95 degrees from the vertical. So depending on how you look at it, some people say, well, it rotates clockwise also, but it basically rotates on its side. You know, what caused that? I mean, that's a gas giant. There's really, in a sense, there's nothing to hit. It's gaseous. So these are mystery questions, great questions to ask. The terrestrial planets like Earth, Venus, for example, may have been hit by something gigantic. One belief about the formation of our moon is that something hit Earth during its molten stage and took a blob of Earth and it became our moon. And maybe it was that impact that sent us tilted on our side at 23.5 degrees. But what flipped Venus all the way over 180 degrees upside down? Something hit it. I don't know. That just doesn't make sense to me that something that big could be hit by something so big to do that. So there's a lot of things we don't understand about the formation of our solar system, from the nebula that it was created, our sun, and then how the materials came together and congealed to form the terrestrial planets and then the Jovian planets. And also, it's a great question. I'm sorry I don't have a specific definitive answer for you, but those are some ideas.
Okay. And if anyone else has any other questions, you know, you can put them in the chat. You can put them in the Q&A. You can ask to raise your hand or something like that. Michelle said, thank you so much, Dave. And I echo those comments because I loved especially seeing that morning of the 17th where they're all in a beautiful line. I feel like that's such a great way to point out that they're traveling in a similar path as well, when you get to see them that close together and recognize that line really does make sense.
It is. It's a real line, the ecliptic.
Yeah. So,
yeah, it's great things to see in April. Stars, constellations, planets, and I really, you know, April really is a month for great planet viewing.
Yeah,
For me, unfortunately, in the morning.
Right, right. That is the challenge. But yeah, I think that was absolutely fantastic. So remember that if you have a question later on, you will be getting an email from me tomorrow, thanking you for participating, asking if you have any suggestions for future topics, those kinds of things. So you can always send me any questions and I will definitely pass them along to Dave to be answered, or you can reach out to him directly.
Of
But
course. astromannh@gmail.com.
that's right. I want to thank everyone for joining us. It was wonderful. I always feel like whenever I listen to your presentations, I discover things that I thought I knew, but now I understand them better. But also there are those moments, about those things that you should really be paying attention to at a specific time. And so I always appreciate your perspective on those.
My pleasure.
I want to thank everyone for joining us. I hope you have a wonderful evening and a wonderful weekend. Hopefully get outside, get a little fresh air, maybe some sunshine. I'm hoping. And we hope to see you in person at some point. But as long as we can do this on a regular basis, at least we get to hang out together and learn something neat about STEM. So good night, everyone.
Thanks so much. Thanks for coming. Bye-bye.